content among themselves without relying on any centralized server. That is, in peer-to-peer, every node has its own connections, so there is no dependency onto the servers. Is this concept clear to everyone, or are there any doubts? Basic meaning of P2P along with the P2P CDNs. Are there any doubts, or should we move ahead? Okay, next slide, please. Now, let us look at some types of the P2P networks. The first one of them, next slide, please. The first one of them is centralized P2P networks. Now, as the name suggests, the centralized P2P network uses a centralized server. But wait, doesn't it sound a bit contradictory? That is, earlier we stated that P2P does not rely on any centralized server. But there's a catch. A centralized peer-to-peer network is a network where peers share data with each other, and there exists a central server to manage the coordination, like user authentication, user logins, along with the peer discovery. And what do you mean by peer discovery? In order to share data from a peer to peer, the node needs to identify the peer within the network so that it can share the data without any flaws. So for that purpose, we have a centralized server. And one important thing to note is that whatever the data is to be shared or transferred within that network, the server has nothing to do with it. I mean, the server has no such files or no such data. The only role of the server is to identify the other peers along with managing the tasks such as user registration and user authentications. Is this concept clear to everyone? If no, we have an analogy. Next slide, please. You can think of it as a central contact book. Assume that there are multiple people and they do not know each other's contact information. But there exists a central contact book which holds the records of every person's contact information. So let's assume if person 1 wants to communicate with person 2, so the person 1 will look into the central contact book and he'll get the contact information of the person 2 so that next time onwards person 1 can directly communicate with person 2 without relying onto the central contact book. So in here, think of this central contact book as the centralized server and person 1, person 2 as the nodes, that is peers. So that the central contact book does not actually hold the conversation or the data that is being transferred between these two nodes, that is person 1 and person 2. But the only role of this central contact book is to map their contact information, or in technical terms, map their IPs and ports. I hope this concept is clear to everyone. If no, you can just reach out with your doubts. Are there any doubts? If no, we can move ahead. Okay, next slide, please. Now, the second type is decentralized peer-to-peer networks. As the name suggests, decentralized peer-to-peer networks are exact opposite of that of centralized ones. In decentralized peer-to-peer network, it is a network where no central server exists, all peers are equal, and each peer can discover, request, and share the resources directly without depending onto the server as that of centralized peer-to-peer network. What we did in centralized peer-to-peer network was the server was the key for identifying the other nodes, right? But in decentralized peer-to-peer network, no such server exists, so that every peer can identify the other peers and can share the data or request the data from the peers directly. So there is no such need of the centralized server, and there does not exist any single authority or entity that controls the entire network like that of the centralized P2P network. So it is the exact opposite of that of centralized peer-to-peer networks. Did everyone understood the concept? If there are any doubts, just let us know, or else we can move ahead. Okay, since there are no doubts, we can move ahead. Next slide, please. Now that we are done with the types of peer-to-peer networks, let us talk about what is torrents. I would like to know if anyone from the audience know what a torrent is. Not necessarily in technical terms, but in general as well. You can just type it into the comment box. Okay, so basically a torrent means the flow. Next slide, please. The torrent means the flow of any liquid. Yeah. So torrent is a strong and fast moving stream of water or any other liquid. So can any one of you tell me how can we map this to a technical term? So as every one of you might have guessed, in technical terms, by we'll replace this water and other liquid with the data so that it will become a fast and strong moving stream of data within the peers. Okay, is it understood by everyone? What do we mean by torrent? A torrent is a strong and fast moving stream of data or file segments within a network within the peers or the nodes. Next slide, please. Okay, now that we have seen what do you mean by a torrent, let us move ahead with torrenting. Okay, so torrenting is a peer-to-peer file distribution mechanism where a large file is divided into several smaller pieces, and those smaller pieces are shared or downloaded simultaneously from multiple peers across the entire network. Okay, this process happens without a single centralized server. So here we use multiple peers that download the segments of the file simultaneously so that we do not need any single centralized server. So in order to achieve this process, we use a protocol that is BitTorrent protocol. Next slide, please. Now let us have a look at the BitTorrent. Next slide, please. Okay, so BitTorrent is a peer-to-peer file sharing protocol as discussed earlier. It is used to distribute the larger files efficiently. That is, we split them into smaller pieces and we share them across multiple nodes simultaneously. That is multiple peers. The basic idea is that instead of having a single server which sends a larger file to multiple users, we use several different nodes to do the same process parallelly. So the core principle is instead of having a single server sending a file to many users, this protocol, that is BitTorrent, allows users to share the pieces of the file with one another, making the whole process parallel. Is this clear to everyone? If no, feel free to reach out with your doubts. If there are no doubts, we can move ahead. Okay, so it is clear. Next slide, please. So here is the basic architecture that we use. Firstly, a torrent file. Torrent file is the file that contains metadata about the torrent. Magnet link, the link used to download without a .torrent file. Seeder, a user who has the entire file, full file. Teacher, a user downloading the file. Swarm, all nodes that are part of the torrent. And lastly, tracker. Tracker is a server that helps the peers to find one another. That is, it has the track. That is, in previous analogy, we had that contact book, right? So it can be used as the tracker. This is the basic architecture that the torrent uses, BitTorrent protocol uses. Next slide, please. Now let us have a brief working of the BitTorrent protocol. Next slide, please. But before that, let us have a look at torrent metadata. Can any one of you tell me what do you mean by the metadata? The term metadata? Data about data. Okay, you're right. Metadata usually means the data about data. So in case of torrent metadata, the torrent metadata is the information that is needed for peers to verify a file in the BitTorrent network. It does not contain the file. It does not contain the actual data. Only the things that are needed to identify the nodes, that is the node to which the file is supposed to be sent, or the node through which the file is supposed to be received. Okay, the torrent metadata describes the file, identifies the swarm, that is the collection, and then verifies the data integrity. One important thing to note is that it never actually contains the actual data itself. It is only to identify the peers. Okay, it is not the actual data. It is just the information that is used to identify the peers within a torrent. Next slide, please. So next point is tracker-based connection. As discussed earlier, a tracker is a central server that keeps track of all the peers that are currently participating in a swarm. So it acts as a central point of intelligence. Since it has the mappings of all IP addresses and ports, it acts as a basic identifier for the nodes that are actually participating into the process. Up until now, is everything clear or are there any doubts? Feel free to reach out with your doubts. If no, we can move ahead. Okay, since there are no doubts, let us move ahead with the working. So basically, first the user downloads the .torrent file. Then after downloading that .torrent file, the peer sends a request to the tracker server, and that request contains the torrent identifier, that is info hash, and the peer that is sending the request, it has the IP address of that peer along with the port number for the sake of the mapping or reachability. Next slide, please. Upon receiving that request from the peer, the tracker server usually responds with the list of the active peers, that is the peers that are actually participating into the process. Okay, so tracker server basically has the list of them, and it basically responds the list, that is active peers or available peers to which we can share the files or can receive the data from. And then upon getting that response from the tracker server, peers can directly communicate with those active peers, other active peers, and can have their transmissions of the data. So basically, the only thing that a tracker server does is holding that mappings and responding with the active peers. So upon getting the list of the active peers, the peer actually connects to them and they can share their data. So this was the entire process. Is the process clear to everyone, or are there any doubts within the process? Okay, then let us move ahead. Next slide, please. Now, upon getting this entire process, of course, there are several advantages and disadvantages. The first advantage would be it is very simpler and faster. So what do we mean by faster discovery is the server sends the list of active peers, right? So a node can have the list and they can reach them. So it is the faster one. And it is also easier to manage. These are the advantages of this process. Then there are several disadvantages as well. Since there is a central server, that is the tracker server, the single point of failure risk arises. That is, if that tracker server goes down, then the entire system collapses. Then the tracker overload is also possible. let's say there is a network of lakhs of thousands of PCs or nodes, and at the same time, many of them send the request and get the response. So there is a possibility of the tracker overload, that is server overload, and it may crash, resulting into the crash of the entire system. Then we have the less privacy. Now, can anyone of you guess why there is a risk of the privacy contamination? Why it is less privacy oriented? You can just type it into the chat box. Okay, user acts as a server, so IP is visible. Okay, not quite, but yeah, could be considered. So basically, the tracker server has the mappings, right? As I told earlier. So each and every time it responds the request with the list of available nodes, right? So anyone can get that information. So it is less privacy oriented. And since we are using a centralized tracker server, it could be less resilient, that is less flexible. I hope the concept is clear to everyone, along with the advantages and disadvantages. If no, you can type your doubts into the chat box. Okay. Now, for the next part, I would like to hand this session over to Dinesh Bungade.
I hope my voice is audible. Am I audible? Okay, yes. So I am audible. So let's get started. So in the previous portion, which Chaitanya took, we actually used a form of torrent, which is basically centralized peer-to-peer network. In that case, we had a central server which actually maintained the list of uh, all the nodes which are near to a peer, right? And that central node was responsible for orchestrating basically everything in that case of torrent. It can seem similar to public CDN, but it is not. Uh, Now let's see distributed hash table. Now, this technique is very important to understand because most of the torrent clients which you see nowadays, for example, if you might have used BitTorrent in order to basically download any kind of file from internet, so they use DHTs. That's why DHTs are very important because they help you to make your network truly decentralized. So let's get started. So DHTs are decentralized distributed systems that provide a key value store across the network of participating nodes, and they are designed to efficiently distribute and look up data across large number of nodes without relying on centralized coordination or control. So, like as I told you, DHTs are truly decentralized networks. So this is the speciality. You do not need to have a central server in order to manage your network. And as you know, hash tables. So hash tables are actually nothing but key value pairs. Basically, if you might have used programming language like C++ or Java, they have the concept called as hash maps, which actually store the key value pairs. So now let's actually see what do DHT stores. So let's move ahead. Kademlia. Uh, so now Kademlia is a distributed hash table. It is a type of DHT which was designed by these two gentlemen, Peter Maimonkov and David Maziris in 2002. So this was nothing but their research paper which they published, and this was truly disrupting because Kademlia actually like acts as base for many modern implementations of Torrent clients, which we use nowadays. So we will actually take a deep dive in Kademlia. Okay, it specifies the structure of network and exchange of information through node lookups, and a more important point, Kademlia uses UDP in order to communicate. Not UDP for actual data transfer, but if they want to like just talk to each other, they can use UDP because like as you know, UDP is faster, and DNS also uses UDP for the same reason. It is because DNS queries should not take HTTP amount of time to happen. They should be fast. That's why we are using DNS for it. Similarly, Kademlia also uses DNS. Cool. So let's move ahead. Before like understanding Kademlia, everyone should be on the same page. So basically, what is a dictionary? As everyone knows, dictionary is nothing but a book where you can like find the meanings of words. And yes, you can like find alphabetical words and each arranged in lexicographical order. So it basically makes your task easier to find the word. Similarly, in computers, we have a computerized version of that dictionary, and as we discussed earlier, it is nothing but a hash map. Hash map stores what? Key value pairs. Suppose if you are giving it a key as an input, whatever it has internally stored as the value of that respective key, it will return it to you. So you can basically retrieve your value with the help of your key. This exact functionality we use in our Kademlia. So what exactly does Kademlia stores? For key, it does not store your node's name or node's IP or anything like that as a value. Because see, IP addresses and things like that, they can like differ very differently. They do not, they actually follow standard order, but it is not very functional for our use case. So what to do now? We are using now hash functions. So I think everyone knows here, hash function actually have this very unique property that no matter how big input you give it, it will always return a fixed output. Right, it will always return a fixed output. Examples of hash functions are SHA-1, SHA-256, and SHA-512. What are the what are the qualities of these? So if you see SHA-256, SHA-256 will always return you an output of 256 bits. Similarly, SHA-512 will always return you an output of 512 bits. So this is a very unique property of hash functions, is that no matter how much big input you give, they'll return a fixed output. So because we needed some consistency in our naming scheme, we use this hash function. So what you'll do basically, whatever identifier your computer has, like IP addresses and things like that, just combine them and give it to a hash function. What hash function will do is generate a unique a hash value that for your computer, and here you go. You get a name for your computer uh, in Torrent, right? So this is a basic use of hash maps in case. But how exactly are we doing? We'll see further. So let's move on. Yes, if you want to locate some information on internet, what things do you need? You need two things. First, the address of the computer where your information is stored, and what exact data do you want? Right, it is very simple. But this very simple thing is exactly a big problem. Why? The problem is internet is very big. You cannot just store the location of the data which you need in your hash maps. Why? The reason being internet is very big. Your computer has its own hardware limits. What if your hash map becomes very huge? What if uh, what if your torrent network basically becomes very big? So you cannot like practically store your entire hash map on a single computer. That would be like just too much for a single computer to handle. You can like actually see how your Chrome browser behaves when you open too many tabs at one time. So yes, how to solve this problem now? Let's see. So as we discussed earlier, if you want to find your computer on the internet where the data is stored, the problem is internet is very big. So in this case, just consider this entire thing as your what you can say internet, uh, and this is your entire key space, and this key space actually represents the data. This is the entire data which this torrent actually shares. Now, your computer cannot store this entire key map, that is key value pairs, key and the data respective, because internet is very big, or the data to be shared, it is very big. How do you solve this problem now? The simplest answer that I can give you, just add more computers, right? Uh, and I think that adding more computers to your system gives birth to the idea of distributed systems. And Kademlia actually is a distributed peer-to-peer network algorithm. So like many computers will actually contribute together in order to help that network sustain. But whenever you are designing a distributed system, main issue comes how to make these things work together, because these computers will not know that how I should exactly work, right? So for that we need some kind of orchestration. Uh, Yeah, and I think you might have heard about Kubernetes. So Kubernetes is basically container orchestrator. Containers do not know how to, like, when should we get created or destroyed. Kubernetes actually tells them based on load, incoming incoming bandwidth, and things like that. So Kademlia actually does that. So let's see how. So these are our two big questions. So the first question is, how are you going to decide which computer will take which part of hash map? That is, the huge data which you want to share, which part of that data should a computer take? Second question is, we have solved this first problem. Second question is, if we ask a computer for a value which is not stored on it, because a computer cannot store the entire key map, then how are we going to get it? These are the two big problems. Okay, so until now, if if there is any doubt, you can ask in chat box. I suppose there is no doubt, so I'll move ahead. Yes, so we will now solve our first question. How are we going to decide which computer will take which part of that huge hash map? It's simple. So as we discussed earlier, we were using hash maps in case of Kademlia, right? So this concept of hash map and hashing is very useful here. Why? It is because Kademlia hashes nodes and data into same ID space, then stores each value on the nodes whose IDs are closest to the data's hash. Let's now understand what exactly the sentence means. So in this case, you can actually see here that you can actually see here this is a 4-bit key space. And can you just tell me how many unique combinations I can form in binary numbers with the help of 4 bits? Just in chat box. Okay. So yes, If you want to create unique combinations with the help of 4 bits, it is simple, right? 2 to the power 4. That is, you can get 16 unique numbers with the help of that. So in this case of example, in order to understand it properly, we are using only 4 bits, but practically we use more number of bits in actual Kademlia implementations. So let's assume this. So now what does it say? Kademlia hashes nodes and data into same ID space. What does it mean? For a ID space, nodes and the data are not treated different. A node and a piece of data can actually have same what you can say ID. Now we actually wanted to solve this problem of which computer will store which data, right? So assume that we have this piece of data called as V6 and we want to store it on a node. What we will do? What we will do is because this V6 data has a node ID of 1100, the closest node which resembles its ID is 1101. So what we will do, we will store this data on this node. You can also store this data here because they are very similar. So Kademlia hashes nodes and data into same ID space, then stores each value on the nodes whose IDs are closest to the data's hash. So yep, we actually unknowingly solved our first problem. Wherever we'll store our data on the node who has the similar or the closest ID. Yes, moving on. Now the question is, how do you find the nearest value? Because like you need to find some way of comparing these because these are nothing but binary numbers. You need some way so that you can actually compare these two numbers. So in order to do that, we are using XOR. Why XOR? I think there might be many questions which are right now arising in your minds. Why are we using XOR? Why not simple subtraction? You will get it. Just stay with me. So a beautiful property of XOR is XOR will return output 0 if both bits are same. If both bits are different, XOR will return your output as 1. And this exact property is of very big use to us. Let's see how. So what we are saying is we are using XOR for distance. Now let's just try finding distances with the help of XOR, not subtraction. So let's see. Let's try to find a distance between this ID and this ID. So let's take a simple XOR. Okay, so first bits are equal, so the output is 0. Next two bits, they are also equal, so the output is 0. Next bits, they are also equal, the output is 0. But the last bits, the least significant bits of this binary number, they are equal to 1. So you can actually see here that it is equal to Euclidean distance or Euclidean distance between these two IDs. But do not mistake this with Euclidean distance. Let's see another example. N5 and N13. Now, if you will compute the XOR of these two values, you will not get 8, you will get 14. And you might ask me like, if it is not equal to Euclidean distance, why are we even using it? We'll understand it later. Uh, Another example. So N7 and N8. These are like two immediate neighbors, right? These are two immediate neighbors. If you are computing XOR here, you'll get a value of 15, which like seems impossible to imagine. It's like breaking mathematics, but we are not breaking mathematics. We are simply computing the XOR. Why? You'll get a hang of it. Just focus. Why to use XOR? The first important property of XOR is distance from self is equal to 0. Yes, so suppose if you are taking an XOR number, if you like XOR it with itself, the answer will be 0, which is also like present in subtraction. Distance to anything else is greater than 0. Yes. And follows triangle property. Like, yes, everyone knows triangle property here. Like dxy plus dyz is always greater than or equal to dxz. Now, what does this like important property helps you? It helps you to guarantee that you'll converge to a node. Why you want to converge to a node? It's because we discussed about this node V6. We wanted a definite place or at least one possible place where we can store this value. So because we are using XOR and XOR actually supports triangle property, so we were guaranteed that we can find a node which will converge here. Because like if we'll try to store V6 on suppose say node 15, its distance is much greater as compared to N13. Right. So anyways, you are actually going to find a node where we are going to converge, where we are going to stop. So you might think like, who is going to tell V6? Just go there and store yourself. Uh, well, we'll see how exactly these things happen. Yes, and as we discussed, it allows you to decide where the value should be placed. Okay, and as I told you, Kademlia distance is not equal to Euclidean distance. But in case of Kademlia, it is equal to length of common prefix between two binary identifiers. What do we mean by this? So let's see these examples which we like saw earlier. In this example, N4 and N5, you can clearly see here the first three bits are same in these two binary numbers, but the last bits are different. That's why we are marking this bit as 1. Similarly, in this case, you can see that first three bits are differing with each other. That's why we are marking it as 1 and the last bits are same, right? So XOR will actually tell you that on which positions the two binary numbers are actually differing to each other, right? So why this is useful? We'll see why actually this is very useful and why are we not using Euclidean distance in order to do these things. Moving on. Yes, so we solved our first problem. Who is going to pick which data? Second problem. If we ask a computer for a value which is not stored on it, then how are we going to get it? With the help of routing tables. Simple, like everything on internet uses routing table basically. Here we will also use routing tables, but a way to visualize these routing tables is very different as compared to normal routing tables which we study. So let's see. So these lines are actually very close to the research paper which the two gentlemen which I named earlier published. So in that they wrote that MDR nodes store contact information about each other throughout query messages. If every node keeps a list of IP address UDP node ID triples for nodes of distance between 2i and 2i plus 1 from itself. We call this list K buckets. The routing table is a binary tree whose leaves are K buckets. So yes, these lines are very unintuitive, but these were present in like that research paper. So I mentioned it here. So let's right now understand this in layman's term, like what is this? So in case of routing tables, there are two concepts: global routing table and local routing table. Global routing table, it stores information about all the nodes which are currently present in your torrent network. And local routing table, it stores information relative to a node. Yes, so this global routing table is not possible in case of decentralized network because of the problems which we discussed earlier. Internet is very big. So we have to find some way so that with the help of local routing tables, with the help of local routing tables, we can do global routing. So Kademlia actually solves this big problem. Let's see how. Until this point, is everyone with me? If there are any doubts, you can ask me in chat box. Okay. I suppose there are no doubts. So moving on, local routing table. So as you might expect that I didn't explain the global routing table. It's because in case of decentralized network, the concept is not existent. So we will study local routing table. So for this part, I want everyone's attention to be with me because this can seem very unintuitive. If you have any doubts, you can ask. Okay, so just see here, this entire thing, you can call it as a global routing table or global scenario. We have these 7 nodes with us and 5 pieces of data with us. Now, assume that we are creating a routing table of N5. Now, uh, as we know, we can only create a local routing table. And this is a simple binary tree. This is not a table, but a binary tree. Yes, it is a binary tree, and binary trees actually solve this problem, or they do not actually solve, but helps us to practically visualize how Kadamlia actually works. So it is a binary tree where every node can actually split into 2 parts, 0 and 1. At every split, you can like do a split of 0 and 1, and depends on number of bits. Here we are four. Here we have four bits, 4-bit ID space. So we are able to do this 4 splits basically, and we are actually going to give them a special name. Just wait. Okay. So if you want to place this N5 here, if you want to place this N5 in a routing table, what are your options? Let's see. So N5 has an ID of 0101. If you're tracing this 0101 here, let's try. So because the first bit is 0, so go left. Now next bit is 1, so go right. Next bit is 0, so go left, and next bit is go right. So you might think that we'll be placing our N5 right here at this place because it is what our logic is telling. But this is exactly wrong. Why? Let's see. So we'll place N5 here. Even though N5's ID was this, we had to place N5 here at the zeroth position. Can you guess why we did this? Just type it in chat box. Okay, so let's see why we actually did this. It is because this routing table is not representing node identifiers or this binary node ID which we gave to every node. What this binary tree is actually representing, it is the XOR distances between 2 nodes. Yes, it is XOR distance. Why? Let's see. If you want to place these other nodes based on the XOR distance with respect to this node 5, we are placing other nodes in our binary tree, right? And we placed N5 here, N7 here, N1, N0, N13, and so on. And we actually missed N15 here. We did this intentionally. Why? It is because we actually fixed here a constant k. Let's see what this constant is. So remember, I told you about buckets. I told you about buckets or k buckets, right? And that in those lines which I actually told you from the search paper. So what are those k buckets? So along this leftmost branch or this leftmost side, every split which you can do, it forms a bucket. It actually forms a bucket. So this entire thing is one bucket. This again, this entire thing is your bucket. Third, this entire thing is your bucket. Fourth, this entire thing is your bucket. So in this case, we have 4-bit ID space. So we are able to create 4 buckets, right? And in each bucket, we will store our nodes, which we found. So in the first bucket, you can only store one node because it is closest to you. In this second bucket, you can store two nodes. You can store more nodes, but they are slightly farther away from you. Here, you can store 4 nodes, but they are more far away from you. And in the last, you can store total 8 nodes, but they are very far away from you. Now you might ask, why is N15 grayed out here? We actually didn't store N15 in our routing table. We straight away said that I will not store it. Why? Because we set a constant here. What we did, we set a constant value is that the number of nodes which are present in my buckets cannot exceed this constant. So last bucket was able to accommodate N15, but we said that we will not do it. Then you might ask me that, won't this do any damage? No, this will not do any damage, but this will produce a very beautiful result. What is that? So the first result is N5 knows more about the nodes which are close to it. What did N5 ensure? It ensured that I should know more about the nodes which are close to me. So like if you see here, this bucket is empty because we didn't have a node. But this bucket is 50% filled. This bucket is also 50% filled. But this bucket, it is not 50% filled. It is very less than that. Why? It is because N5 knows more about the nodes which are close to it, and N5 knows much less information about the nodes which are far away from it. And this property actually prevents exponential growth of buckets because we saw here that we had one node capacity here. We had two nodes capacity, we had four nodes capacity, we had eight nodes capacity. This is increasing exponentially. So in order to stop the exponential growth of our buckets, what we are actually doing is we are restricting that I will not fill more nodes than two. Now you might ask, N15 is like gone, so how can I find it? It is very simple because we draw here N5's routing table. But because I told you we are using XOR distances in this case, and as per the XOR distances, we have N13 in our routing table. And if we see our global scenario, N13 is very close to N15. So what can our node 5 actually do is it will ask N13, hey N13, do you know N15? And because N15 is very close to N13, and 13 will say, yes, I know him. So even though we didn't store N15 in our routing table, because N13 in N13's list of peers, N15 was present. So we got the address of node 15, even though we didn't have the even though we didn't have the N15 present in our routing table, because we knew a peer which is very close to it in our existing routing table, we were able to actually find a node which is not present in our routing table. This is the magic of Kademlia DHT. And uh, Kademlia actually achieves this in big of log n time complexity. Why? It's because this simple property of XOR. What we are actually doing in case of XOR is we are actually comparing. Yes. So in case of XOR, we are doing nothing but comparing where our bits actually differ. So in this case, or let's assume this case. So the first two bits are very different. So we know that uh, in case of binary search, if you know binary search, each iteration of binary search eliminates half of the search space. Similarly, whenever we are like comparing per bit by bit, we are actually reducing our search space by uh, this entire height of binary tree, right? So that is why we are actually using XOR and not why that is why we are using actually XOR, not Euclidean distance, because Euclidean distance will not give you this property that you can do big O of log n routing, right? So per bit, you are reducing your search space by literally half. So that is why we are using XOR. And why we are not using Euclidean distance, it is because it is very vague in this terms, because see, the problem is we do not know where exactly our nodes are on the Earth, because Earth is very big. So Euclidean distance do not make sense using in terms of internet, because nodes can be like way too close or way too far. And to solve this problem, we are not actually considering here physical distances between the nodes, but we are only dealing in terms of these IDs. And these IDs are allowing us to do big O of log and hop routing. And let's simulate. So as I told you earlier, let's simulate. To find k, suppose if you want to find this value of k in your torrent, so how you will do it? So if you want to find this value of k, the nodes, and we also have a node r. Like this node r is a requester. It wants to find this value of key. It does not have it in its routing table, so it is basically asking the torrent network, does anyone know where does this key lives? So because R knows N1, N2, and N3, what it will do? It will compute XOR distances. It will compute XOR distance of N1 with K, and N2 with K, and N3 with K. Whatever the nodes which it is actually known, it will compute the XOR distances with them. So what we found out is that node 3 was the closest so far, which R knew. It is because you can actually see here the first two bits are same in case of N3, and it actually matches the value of K here. And we'll see how to deal with later bits. So because we now found that N3 is the closest, we will now ask N3. R will ask N3, hey N3, which nodes do you know? Or do you know the value of K? So like N3 does not know where does the K live, but it knows these two nodes. So it will return these two nodes. Now N3 will, because these two nodes are returned, will repeat the same process. With N4 and N5 will compute XORs and see the beautiful property of XOR. We found a node which had most closest XOR value. Now we'll do another iteration, because we had N5 which resembled it more closely. We'll now ask N5, hey N5, do you know K? It does not know it, but it does know a node. So It will return the node ID of this node to R. And what R will do? R will compute the XOR. So now we found out that this was even more close. Like last time it was 2, and in this case it is only 1 bit away, right? So we'll again try to repeat. Ask N6. Hey N6, do you have the value of K? So N6 will actually return the nodes, but because we saw that XOR actually follows the triangle property, we are guaranteed that we will converge on a single node. That's why whatever node you will now compare your XOR, you will always find an XOR which is greater than or equal to 1. That is why no improvement, and we'll stop here. Triangle inequality at work. And we now know that N6 should definitely have the value of K with it. This is how we understood two things. We understood that our data will be stored on the node which is closest to the node which has ID similar to the data's ID, right? And second thing is, if you want to do routing, you can easily do it with the help of XOR, right? So, like you might now ask me, like, how performant is this? Because every system's performance, like testing should be done. Testing should be done. So now, if we see here, theoretically, for a million nodes, you will need log base 2, and a million is 10 lakhs, so you'll need nearly 20 hops in order to find your node. But in real world scenario, on an average, you only need 6 hops in order to find your node. Can you like imagine this? You have 10 lakh nodes, and if you want to find your data, you can only find it within 6 hops. And for a billion nodes, billion is 100 crore nodes. So practically, you will need only 5 to 8 hops. Why this is so? Because practically, we use 160-bit ID space, and the value of k is equal to 20, like the number of nodes which are present in per bucket. We are limiting that value to 20. So now you can see here that our buckets are actually very dense. And because our buckets are very dense, there is a very good chance that you'll find your node uh, you'll find your node very easily. You will not need to do these 20 hops, or in this case, if you compute this logarithm, you'll need 30 hops, which is theoretically, which is actually very good for a billion nodes. But still, you'll practically only need 5 to 8 hops. So you can see why torrents are so powerful. Why you can actually see, because if you're like trying to download if you're trying to download a file from torrent, you will generally notice that you can download it very easily and very quickly as compared to normal downloads from websites. It is because of this magic. We are not relying on a central server. Nodes are actually helping each other in order to transfer the data. So yes, so we'll also simulate another thing. Suppose we have three old nodes, A, B, and C. Now X is a node which is a new node, right? It is a new closer node, but it is a new node. It does not know anyone, right? Now, in case of R is a requester who wants to find the value of K. So now, R will basically ask the network, I want to find the value of K. So lookup will actually naturally reach K because lookup will naturally reach X because it is a more closer node, because like we saw the triangle property, right? R will now ask X, hey X, do you have K? Because X is very new, X will return to reply to R, no, yeah, I do not know the value of K, but here are the nodes closer to K which I know. Now R has the data of K and a list of the K closest nodes returned during the lookup. Why now it has the data of tk? Because x knew like some nodes which were closer to it, and they actually had the data. So because they were old nodes and x is a new node, so R actually got the data from those nodes. Now see a beautiful rule of Kademlia. What R will do is R will actually now take the initiative of storing this data on the variable x, because it knows that x is a new node which has ID which is closest to this data, right? So R will actually store this key value pair in the x, and x has to accept it because it is part of network and stores it. The requester R is the one that takes the initiative to store the data on X. Why? Because Kademlia's rule is after a lookup, that is, after you have received the data, the node that has the data must ensure that the k closest nodes have it. That is, X was in the k closest nodes in its list. So it was R's responsibility to store the data in those nodes if they didn't have it. So this is how Kademlia network works. And yes, great distributed systems embed global properties. Great distributed systems embed global properties into algorithms that work locally. This is a very beautiful property because uh, we are not using any global view or a global routing table, but with the help of algorithms which are working locally, we are able to do global routing. And Kademlia is one of those beautiful algorithms, right? So yes, I know it is very hectic to understand this. So if you have any doubts, you can ask in chat box. Okay, so I believe there are no doubts. So let's move on. Yeah, next. Now yes, so this is not another distributed hash table. No, Kademlia is the only one which we are going to see, which we saw. But now PEX, it is a gossip-based mechanism where peers share recently discovered peers with each other. Now, before understanding PEX, uh, things which you should keep in mind is that it is not a routing protocol. It does not use XOR for distance calculation. There are no lookup queries, and there is also no global view of your network. So, what does actually PEX do? Suppose if you are like recently joined to this network, because you are new to the network and there is no central administrator or central server which you can ask like to tell me my peers. So like for because of that reason we need some technique so that we can like expand our cache or our routing table, right? So PEX actually does that. So now what in case of PEX, what every node will do is every fresh node, a node will ask suppose let's see with example. Let's understand this is more better understood with the example. So in this scenario, we have 5 nodes of the network. A has recently joined the network. It only knows B. B knows 2 nodes, D and C. C knows 2 nodes, B and E. A wants to now expand its routing table, right? So what will A do now? Let's simulate PEX here. So A will ask B, hey B, which 2 nodes do you know? What B will tell is, I know D and C. So these 2 nodes will naturally reach A. And yes, A will now add them in their routing table. So C simply, with this simple technique, we expanded our routing table, right? Now, because A now knows C and D, it will ask them also, hey D, which nodes do you know? Now D will return, I know A and B, but these are trivial because they are already in A's routing table, so they are of no use to us. But in case of C, in case of C, C knows B and E. It knows B, it is trivial, but it knows E, which is a new node. So it is of use to us. So what we'll do is we'll add this E to A's cache, X cache. So this is how your entire routing table basically expands itself, right? So if you're like freshly connected to a network, X actually stands for peer exchange protocol. So this peer exchange will help you to expand your like routing table if you're newly joined to the network. And then you can also like after getting this data, you can help another node which joins to the network. Suppose if there is a new node which joins, then we can actually help it by giving the data which nodes it knows. So this is how basically a torrent works. It does not work. It does not work on selfish behavior. It works by sharing and caring. So yes, these are the basic two differences between DHT and PEX, that is peer exchange. So the first difference is DHT is used to find your data and your peers in a network. It is used to find. On the other hand, PEX is used to spread the information about peers, right? Secondly, it uses XOR distance metric. PEX actually uses no distance metric. You'll only return the peers which you know. You'll not use any distance kind of metric here. XOR is only used by DHT. We use structured routing. We saw the concept of K buckets. Every bucket represents the distance, the XOR distance from our local node, whom the routing table is. So it is a structured routing. But in case of text, it's just unstructured gossip. You are just simply telling, I know these nodes. If you wish to add it into your table, just add it. Yes. So, and the last is bootstraps from zero. Yes, this is a beautiful what you can say strength of Kademlia. Not a strength actually, but the thing of Kademlia is that it can bootstrap from zero. Suppose if you are like starting node of your torrent network, so in that case, DHT can work, right? But in case of PEX, suppose if you're like joining to a new network, you need some peers because as we saw earlier in this example, A was freshly joined, but at the starting point, it knew B. It knew B as its neighbor. That's why you need at least one peer which you can talk to so that it can share the information with you, right? Yes. So these are now some basic optimization techniques which torrent networks use for bitfield. Bitfield is a bitmap sent by the peer that shows which pieces of torrent it has. Now, like as we discussed earlier in Chaitanya's part, your entire file will not be shared as is. It will be split it into multiple parts, and those individual parts will be shared. Now, a bit field is simply it is represented in terms of ones and zeros. So now, by one, it means peer has the piece. Zero means peer does not have that piece of data. So suppose if your entire torrent has 8 different pieces, the bit field will be 10110010. So what does it mean? Suppose if I'm asking a node and it returns me this bit field, so this bit field tells that that node has first piece, but it does not have second piece. It has third piece, it has fourth piece, but it does not have fifth and sixth pieces. But it has seventh piece and eighth piece it does not have. So this is what they are actually doing when in case of PHT Kadamlia, when we are asking a node like, do you have the data? So they are actually exchanging these bit fields with each other. So in order to understand or in order to know which piece of information do they have and they do not have. Next is Tedford algorithm. As it stands for, you will only get the data if you give the data. As simple as that. Because like there are many users who just join a torrent network for the purpose of basically downloading the file. As soon as their file gets downloaded, they basically stop their torrent client and stop seeding. That is helping the network. Uh, this algorithm actually punishes them. It ensures fairness in this form. Peers upload to those who upload to them. I will only share the data with you if you're like being helpful with me or if you're being cooperative. Yes, best uploaders are unchoked periodically. Suppose you are choked by you were choked by a node and you have like basically improved your credit score here. That has improved your reputation. Uh, so the nodes which have blocked you, they can actually unchoke you. So yes, these things can happen in case of a torrent network. One peer is optimistically unchoked to discover new partners. So this is basically a bet kind of thing. One peer will be optimistically unchoked to like discover new partners, and it discourages freeloading. That is like just doing torrenting for your own benefit and not helping anyone. Next is rarest piece first. Maintains the piece availability. Suppose because like as we discussed earlier that your file is the broken down into multiple portions, there can be some scenarios where that the data, like some pieces are rare in your network. They are not present in many nodes. They are only present in few nodes. So in such cases, what a client will do is, suppose if you're requesting a file from torrent, and that file is like broken down into different pieces, obviously. So your torrent client will try to fetch those rarest pieces first. So where we are actually like achieving two goals. It prevents rare pieces from disappearing from the network, like getting extinct completely, and ensures even distribution of data. Why even distribution of data? It is because if you have received that piece, you can actually help someone else with the help of that piece. So you are now becoming a seeder for that piece of data. And obviously, it will improve the overall download speed of the network. And it is the rarest, rarest piece first algorithm. Protect the rarest pieces. Next, simple seeding strategies. Rarest first seeding helps to spread the scarce pieces. Round robin, serve peers fairly, and superseding only reveal pieces gradually to avoid duplication helps to force other peers to upload their peers rather than single seed uploading to all peers. What does this mean? Suppose if you have a network of 5 nodes with you, and you only have you are the only node which has the piece of data. Now, what will your node do is, it will, instead of sharing with all 5, you will share with only one. And you will now expect that that node which you just shared will now share it with other people. So what does this help in? It helps in like distributing your data to your network evenly, and it actually forces other peers to upload their information rather than like pressurizing one peer, like uh, it should only share. So these are some seeding strategies. Yes, so this was it. This was it for this session. We'll just take a quick recall of what did we saw. So we understood peer-to-peer networks. Then we moved to types of peer-to-peer networks. Then we understood BitTorrent protocol, and under this protocol we understood Kademlia, XOR routing, K buckets, and concepts like that. We also saw peer exchange. And then we saw various techniques to improve the what you can say overall performance of your torrent network. Yes. So in this season 6 of FOSS files, we explored torrent-based CDNs, which was the session. So torrent-based CDNs are best when huge files are downloaded by many users. Cost must scale down with popularity. Content is static and non-interactive, and users can tolerate slower startup. So yes, the best use cases, if you have ever dual booted your computer, there is a good chance that you have downloaded your ISO file with the help of a torrent client like BitTorrent or QBitTorrent if you want a fully open source version. Game installers and patches, if like there are some uh, groups which can actually share retro games, so they can actually share with the help of game installers. Uh, Sorry, they can share with the help of torrents. Uh, Academic datasets. So yes, academic datasets can be very big. So these torrents are a good way to share them. Public CDNs. We also discussed public CDNs in this season. So we saw that they are used when low latency matters, content is streamed or interactive. In case of Netflix, you will not use a torrent. You have to maintain your public CDN because you will know the behavior of your network. P2P Academia's behavior uh, is not entirely guided by the people who have hosted that torrent network. Network decides itself what to do. Yes, security, strong security and control are required, and users use standard browsers. So yes, this is a big point because browsers everyone have, but many people do not have a torrent client. So if you want to be a part of a torrent network, you need to have that torrent client which you can like ask stuff and do like that. But in case of public stadiums, you can like basically use a standard browser which you are right now using in order to watch this live stream. Examples are video streaming, websites as APIs, and software as service. Yes, so thank you. Like this was the end of the session. If you have any doubts, you can ask in chat box. Okay, yes. So Bhargav has asked, does nodes in Kademlia store actual data or just IPs where data lies? Uh, the nodes will actually store both. Uh, Both meaning, suppose if you have a routing table with you, local routing table. So in that local routing table, you will not store actual data. You will only store the peers which you know about. But those actual nodes will store those keys and actual data. So both things will be stored. And as I told you earlier, that data whose key is closely resembling to a node, it will be stored on that node. There is no other technique, no other special technique which we use. We are actually dealing in terms of these node IDs. If it is closest, then it should go on this node. Simple logic. In case in routing tables, you will store IP addresses. Yes. So if we have just downloaded a piece of data and now I want to act as a seeder, but XOR distance from hash of that data is large, will I be able to act as a seeder for data? Uh, no. See, you will only have that data if your hash value is like very close to it, or if you are the only one in the peer. Uh, or as we saw earlier, that if someone detects that you are the closest node, you are the closest node in their routing table, they will take the responsibility that they will take the data to you. So you can act as a seeder, but as we saw that X, let me take you that let me take you that slide. Yes. So in this slide, uh, R actually now gained the data, but at this point also, when R was asking X, you have K. X didn't have the value, but uh, because R actually now detected that X is nearest in my routing table of K closest nodes, then R will actually take the responsibility that I will store that node into that node. And in this example, which you just told about, you can act as a seeder if and only if someone asks you. If someone is not asking, you will just stay. You'll stay. What you can say. You will not do anything basically. You will just wait. That let someone ask me. Is it out clear? Any more doubts? Yes. So I see no more doubts. So I think it's time to conclude. Uh, yes. So basically, we just finished our season of FOSS files. It was season 6. We have been conducting, our club has been conducting multiple seasons. So this was the sixth iteration. Uh, Here we covered CDNs. So like stay tuned for upcoming sessions of FOSS files, which our club will be conducting. So yes, thank you. Thank you.